Welcome to Lesson 8B, Room Ventilation with Wall Adsorption. We're going to talk about simple room ventilation with something additional here that's called wall adsorption. We're going to keep getting more involved with these room ventilation problems. First of all, what do we mean? This is when you have walls. It could be walls, it can be furniture, it could be curtains, rugs, anything that adsorbs the contaminant. And so we're talking about adsorption into the surface, and I wanted to just quickly tell you the difference between adsorption with a D and absorption with a B. Adsorption is what we're talking about here, is that the vapor molecules attach to a surface. So they're attracted by surface molecules and they attach to it. A good example would be charcoal filters that adsorb odors and other molecules of contaminants. Absorption is when vapors dissolve in a liquid. For example, CO2 can be absorbed into water and you can make soda pop, for example. I like Mountain Dew. I like Coke, dude. I'm a Barks root beer man myself. When I drink soda, it comes out my nose. Let's look at our simple room. We have the same drawing that I had before. The only thing new now is this wall adsorption term. From now on, I will use CS instead of CA. CS is not always equal to CA. CA means it's coming from the outside air ambient, whereas CS is supply. And in general, unless you have a window open that you're blowing air in directly from the outside, this is typically coming from a ventilation system that has filters and has some recirculated air. This wall adsorption is what we want to talk about now. Wall adsorption, or plate out, or wall loss. I kind of like the wall loss the best. It's the easiest to remember, and that's exactly what it is. It's a loss or a sink of contaminant. It's actually a way to remove contaminant from the room. You have this source that's putting this chemical into the room. It's getting all mixed up because it's well mixed. Some of it goes out and some of it gets adsorbed. We'll typically just draw one place here, but this can be on walls, it can be on curtains, on rugs, it could be on furniture in the room, any surface that can absorb that chemical. Recall that S equal a production term, and here wall loss is a negative production. In other words, it's a sink. And when you deal with differential equations like in fluid mechanics, which is my specialty, we're always talking about production and sinks. Some examples of this would be hotels or cars with smokers. Now, when I was growing up, people could smoke in hotel rooms. Now, I guess there's still some smoking rooms that you can order if you really want to. But if you've ever been in a car or a house, apartment, or a hotel room where people have smoked, you can really smell it. Smoke gets into especially cloth things like drapes, clothing. You can smell it on people that have smoked. Their clothes smell like cigarettes. All these surfaces adsorb tobacco smoke, and then they later desorb it. When there's no smokers, then the surfaces desorb the contaminant. In this case, tobacco smoke, and all other chemicals work the same way at different rates. You can adsorb and then you can also desorb back into the room. So once that happens, this desorption becomes a source of the contaminant back into the room. One time I went into a hotel room and I signed in and went to the room, and it smelled so much like smoke I couldn't stand it. And so I went back and got a different room. Some of the smoke can stay in the room, in the materials, for months before that finally desorbs out. What's the equation for this wall loss term? M dot of the wall loss is equal to KWAS times C. That is what I drew on the diagram. We have three parameters here. Of course, C is the mass concentration. I'm dropping the J subscript. AS is the surface area of the adsorbing surfaces. And then this is the mass flow rate of the pollutant, not the bulk air. We're dropping the J subscript that we normally have. And then this KW is the new thing. This is called a wall loss coefficient. It's also called a deposition velocity or an adsorption coefficient. So there's three different names for that. I like to just call it a wall loss coefficient.
Why is one of them called a velocity, dude?
Good question, Joe. It turns out that the dimensions of kW are length over time, which is why we call it velocity. And if you check the dimensions here, m dot would be mass over time. This would be L over time. And then area is L squared. And then C is a mass concentration. So this would be m over L cubed. And when you put all that together, you see the L's cancel and you end up with m over T. So that checks out. So that's the equation. When we add this loss term as a sink or a negative production term, it comes with a minus sign. And we just added that to our previous equation for this simple room ventilation. So we have V dc dt equals what's coming in. This is the source, and then this is what's going out, and then this is the wall loss. So other than that, it's the same equation we had before. We just have this extra term, which is a wall loss term. What you're going to have to get in the habit of doing is looking at a diagram like this when we start putting in air cleaners in here. We'll have open windows, we'll have recirculation, all kinds of things happening as we get more complicated. But you'll have to look at this and say, okay, what do I have coming in and what do I have coming out? I have QS coming in with some CS, so there's some contaminant coming in. There's a source that's bringing in more. And then what do I have going out? Well, CE is always C because we're assuming well mixed in here. So there's some of it leaving through the air, and then there's some of it leaving through this wall adsorption term. So that's why we have two positive terms here and two negative terms here. You see the text for empirical equations for KW, this wall loss coefficient, and you have different equations for vapors and for particles. Now, we're not dealing with particles so much right now, we're dealing with vapors mostly. In this course, we'll either be given KW to solve a problem, or that'll be maybe sometimes your parameter that you're solving for. The solution, well, this is a first order ODE. It can have constant or non-constant coefficients, just like previously. C itself is a function of time only. And Q, S, KW itself, AS can all vary with time. If it has constant coefficients, we can solve analytically. If not constant, we solve numerically with the Runge-Kutta technique or some other marching technique in time. And so how do we solve an equation such as this? Well, the key is to separate terms with C and terms without C. Every time we add something to our room ventilation to make it a little more complicated and a little more realistic, you're going to have to do this. In this case, I look at my equation above at the top here and I see CS and Q, that doesn't have a C in it. S doesn't have a C in it, but this one does and this one does. I'm going to divide through by V, also the volume. So dc dt is equal to S plus Q CS over V minus Q plus KW AS over V, and that's all times C. So it's the same equation. I divide it by V and I just regroup things. And now I can rewrite it in standard form, as you recall. So obviously, S plus QCS over V is equal to B, and Q plus KWAS over V is equal to A. Once we have these, we can solve. So if A and B are constants, then we have the same solution as before, CSS minus C over CSS minus C naught, the initial condition, equal E to the negative AT. That's all there is to it. It's the exact same equation we had before. So that's why in all these kind of first order problems, once you get A and B, you're home free because you can just plug them into this equation. CSS itself is B over A. Here, turns out that CSS is equal to S plus QCS over Q plus KWAS. So this is again the same as previously, except we have this extra term due to the wall losses. You have this equation only if A and B are constants. If A and B are not constants, we still solve this equation, but we have to do it numerically. I want to do an example, room ventilation with wall losses. Let's suppose we have a source of contaminant that starts at T equals 0 in a room that has wall absorption. I'm just going to label these things. Wall adsorption coefficient, this is our KW, is given. And then finally we have AS. This is the surface area of all materials that absorb the contaminant. We want to estimate the mass concentration of the contaminant when it's reached steady state conditions. Our equations, CSS equal S plus QCS over Q plus KWAS. So that's our answer in variable form. The only other thing I need to do is that plug in that Q is equal to N times V by the definition of number of room air changes. And when you plug everything in, CSS equal to 3 digits, 7.55 milligram per meter cubed. I wanted to briefly mention desorption. This equation, m dot wall loss is equal to KWASC, is for adsorption only. So the question is, what about desorption? In other words, when it comes out of the wall or the curtains. This is what I was talking about when I went to the hotel room. Nobody is actively smoking, but you can smell it. You can smell smoke in somebody's car that was smoking or on their clothes. It's desorbing at that point, going back into the atmosphere. Adsorption, remember, was a sink out of the room, whereas desorption is a source or a production into the room. In the equation, this m dot wall loss appeared with a negative sign. So we want something that's going to appear with a positive sign for desorption. There's plenty of people that have studied different ways to do that, but the simplest equation is a slight modification of the one I just wrote, KWAS as above. And instead of just C, we have C minus some C sub D, where C sub D is a concentration that determines whether it's going to adsorb or desorb. If C is greater than CD, in other words, the concentration in the room is bigger than some CD constant, then m dot wall loss is positive, and this would be an adsorption, and this would be a sink in terms of the room. It's a loss or a sink. And if C is less than CD, so if you have fairly clean air, it'll reverse itself. So m dot wall loss by this equation becomes negative, and that's a desorption or a source.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.